Hello everyone, my name is Rohit Singhal and we were discussing about redox reactions. In the previous classes, I have studied with the types of redox reactions. So, we have discussed a few types in the previous class, types of redox reaction. Okay. In the previous class, I have first discussed about the combination reaction. What I have discussed in combination reaction is combination reaction to happen, combination reaction to be a redox reaction, at least one of the reactants should be present in its elemental form. The example I have discussed is the combustion reaction. Any combustion reaction, it means burning an element or compound in presence of oxygen, it is an example of combination reaction, redox combination reaction. Okay. The second I have discussed is displacement reaction. No, the second I have discussed is decomposition reaction. Okay. What happens in decomposition reaction? It is totally opposite to what is combination reaction is. Combination reaction, two or more than two elements or let us say reactants combine to form a product, whereas in decomposition reaction one reactant dissociates itself into more than two products. For example, I have discussed is water on heating can dissociate in hydrogen gas and oxygen gas. Okay. Dissociates the water molecule dissociates into hydrogen and oxygen gas on heating. So, this is an example of decomposition reaction and it is also a redox reaction. As you can see, the hydrogen goes from a +1 oxidation state to 0 oxidation state, whereas oxygen goes from minus oxidation to -2 to 0 oxidation state. Okay. The third I have started is displacement reaction. Displacement reaction. Displacement reaction I have discussed are of two types, one is metal displacement, another is non metal displacement. Okay. Now, what happens in metal displacement? Metal displacement I have discussed one classic example of copper sulphate plus zinc, where zinc displaces copper in the copper sulphate solution to form zinc sulphate and copper. Okay. This is also a redox reaction, as copper goes from +2 to 0 oxidation number and zinc from 0 to +2 oxidation number. Okay. So, zinc getting oxidized and copper getting reduced. So, this was the example of metal displacement reaction. Non metal displacement reaction, this I have started during the end of the previous lecture, is non metal displacement reaction. Now, what this non metal displacement reaction is? Non metal displacement reaction includes hydrogen or oxygen displacement through the evolution of H2 gas or O2 gas. The hydrogen or oxygen gas has been released in such kind of non metal displacement reactions. Okay. For example, I have discussed the very strong alkali metals, react with cold water. These very strong alkali metals are very strong metals and this react with cold water to form the alkali hydroxide. For example, sodium reacting with water molecule to form sodium hydroxide and then hydrogen gas has been evolved in such reaction. All these reactions I am writing here is the redox reaction. You can see by the calculating the oxidation number again, sodium oxygen getting from -2 to hydrogen going from +1 to a 0 oxidation number, whereas sodium going from 0 to +1 oxidation number. Okay. This strong alkali metals, however, the alkaline earth metals, that means group 2 metals. These group 2 metals are also very strong metals, however, these are comparatively less stronger metals as compared to the group 1 metals. So, group 1 metals can react with cold water, however, these metals, these alkaline earth metals reacts water on heating or reacts with warm water to form the hydroxide and hydrogen gas. Okay. This alkali metals and alkaline earth metals can react with water to form this hydroxide and the hydrogen gas evolution. There can be some other metals also that does the same. For example, iron does react with water on heating to form iron oxide, it forms iron oxide, not iron hydroxide, and H2 gas is been released. Okay. Iron has gone from 0 to +3 oxidation state, whereas hydrogen has gone from +1 to 0 oxidation state. That means, iron is getting oxidized from 0 to +3 and hydrogen is getting reduced from +1 to 0. Okay. So, these were the examples. Till now I have discussed about the non-metal displacement reactions. Okay. However, there are many metals that are not been able to react with water, but they can release hydrogen gas still, but by reacting with the acids, or we can say less reactive metals. Less reactive metals on reaction with acids can release the hydrogen gas and being part of a non displacement reaction. For example, zinc reacting with HCl to form zinc chloride and hydrogen gas. The metals that can react with water and release the hydrogen gas, those release hydrogen gas with water and can also release hydrogen gas with acid. For example, Fe, iron on reaction with hydrogen chloride gives this reaction. Similarly, magnesium, all these are redox reaction. However, zinc on this is a lesser reactive metal, This is a lesser reactive metal and it does not react with water to form hydrogen gas. However, it can react with acids to release the hydrogen gas. Okay. This reaction is one of the more important reactions in laboratory. Synthetic chemists use this reaction to produce hydrogen gas in the laboratory. Okay. This is one of the reactions that is prominently being used in the laboratory to form the hydrogen gas. Okay. Now, these lesser reactive metals that are reacting with acid and not with the water to release hydrogen gas. Okay. Now, you must be wondering that why it is so that some metals are reacting with water to release the hydrogen gas, whereas some metals are reacting with both water and acid to release the hydrogen gas. This is the same case which we have discussed for the preferential oxidation. You remember preferential oxidation that why zinc is able to replace the copper sulphate solution. However, the copper is not being able to replace the zinc sulphate solution, no reaction happens, that copper sulphate does not form. Why it is so? That it is so because zinc, there is a reactivity series of metals, reactivity, there exists a reactivity series, that means which says that zinc is more reactive than copper and which in turn is more reactive than silver. This I have discussed with you in the previous class, where we have discussed about the preferential oxidation or preferential oxidation, right. That means zinc is a more reactive metal, that means zinc will preferentially go into the positive oxidation state or will preferentially oxidize, whereas silver will get reduced. Okay. Preferentially, or zinc, if I say in a more layman language, it prefers oxidation. Okay. Now, as there is a reactivity series for the metals, there also exists a reactivity series for the halogens. Halogens, that means group 17 elements. Group 17 elements. What are the group 17 elements? Fluorine, chlorine, bromine, iodine, right. Okay. What is the reactivity series on these halogens is? This is when we go down the group, the oxidizing or say the power of the halogens as oxidizing agents decreases. Now, what does it mean? We know halogens generally exist in negative oxidation state. Fluorine only exists in -1 oxidation state. Why? Because fluorine is the most electronegative element known, and it can't have a either it can have a minus oxidation state, that is -1, or it can have a 0 if it present in F2, means elemental form. Okay. It cannot have a positive oxidation state. That means fluorine will always tend itself to go into a -1 oxidation state. That means it will always be ready to get reduced, and if it is getting reduced, it will be what? Oxidizing agent. Remember the concept of oxidizing agent, reducing agent. The element that gets reduced is called oxidizing agent, and the element that is getting oxidized is called reducing agent. Okay. So, fluorine wants to get reduced, that means fluorine is a very good oxidizing agent. Or in fact, I can say strongest oxidizing agent. Okay. That means that fluorine has a more tendency, F2 has a more tendency to go into the F minus. How will I see through the examples? Let us see, where we will be needing to compare the reactivity series of these halogens. Let us say the chlorine is reacting with the KBr solution. Okay. Remember, fluorine, chlorine, bromine, iodine, which one will tend more to go into the minus oxidation state? Chlorine more than bromine. That means, this chlorine will replace the bromine in KBr solution to form KCl and Br2. Similarly, this Cl2 can also replace the iodine in Ki solution to form Ki and I2. However, if you ask that Br2 reacts with KCl and it forms KBr plus Cl2, no, this reaction does not happen. Why? Because chlorine has the more tendency to remain in -1 oxidation state. It will not go into 0 oxidation state in presence of bromine, because there is a reactivity order that says that fluorine is a better oxidizing agent, then chlorine, then bromine, and then iodine. That means, fluorine will exist in minus oxidation state. If not fluorine, then chlorine, then bromine, and then iodine. This reactivity series you have to remember, so that you will be able to understand this reaction, that why one reaction is going and why another reaction is not. Okay. So, there exists a reactivity series for the metals, which I have discussed about zinc, copper and silver, and I will also discuss the entire series in the next class. And this about the halogens, where I am discussing that the halogens also have a reactivity series, where fluorine is the most or the strongest oxidizing agent in the periodic table. Okay. This I have told that which in presence of what will go into the in the negative oxidation state and which in the positive oxidation state. That means, Br2 in let us say if I say all the reactions if I discussed, fluorine will always exist in minus oxidation state in presence of any halogen. Okay. Chlorine minus can react with bromine minus, react with iodine minus to form, or chlorine in presence of fluoride only it can form the fluorine gas, chlorine Cl2. Because fluorine is a more oxidizing agent. So, only the chlorine will go into a 0 oxidation state only in presence of fluorine, whereas bromine in presence of chlorine in presence of fluorine will go into the 0 oxidation state. Okay. Iodine reacting with F2 Cl2 or Br2, it will form I2 and the respective F minus, Cl minus and Br minus. This is what I want you to guys understand, that what this oxidizing agent reactivity series of halogen means, that fluorine will react will present in minus oxidation state in presence of any halogen, whereas chlorine, because it has a because fluorine only has a more oxidizing or a better oxidizing agent than chlorine. So, in presence of fluoride ion, fluoride F2 can go into the F minus, and similarly for bromide and chloride I have discussed the things. Okay. There also if I say one is halogen displacement. This is nothing but the halogen displacement. What I have discussed is halogen displacement, that one halogen is displacing another halogen. That means, that any solution of chloride F2 can replace that solution. If I say any, let us say A Cl minus, A I am using any metal, let us say any metal is there, and fluoride F2 can replace to form AF plus Cl2. Okay. So, this is nothing but the halogen displacement, and which halogen will displace and which halogen will not be able to displace the another halogen, that we will discuss, that we will be able to understand on the reactivity order. That means, F2 Cl2 Br2 and I2, power of oxidizing agents. You just have to remember one thing, that fluorine wants to remain in the minus oxidation state, whereas then chlorine, then bromine and then iodine. This is the reactivity order, and then you will be able to solve or the comprehend entire halogen displacement reactions. I think one of the reactions we have left, that is disproportionation reaction, and then we will start up with the balancing of the equation. One of the most important things of this chapter will be how to balance the redox reactions, that we will discuss in the next classes. Thank you.